So let's now talk about photometric stereo, which is a method we've already discussed in detail. We'll quickly summarize the basic idea behind photometric stereo and see how we might actually extend this idea. So what is photometric stereo? In the case of photometric stereo, the idea is very simple. It is to capture multiple images of an object under different known light sources. The light sources are in different directions with respect to the object. And we assume that the object has known reflectance properties. These reflectance properties are known to us either in the form of an equation, the reflectance model fully described with all its parameters, or we can use calibration objects, as we saw earlier, in order to understand what the reflectance properties are and represent the effect of the reflectance properties in terms of lookup tables. But irrespective, we know the reflectance properties in this case. So when you do that, you can actually use these multiple light sources, take a stack of images, and then compute the surface normal at each point on the surface. And in the context of photometric stereo, our goal previously has always been to minimize the number of images that we want to capture. So for example, we showed that in the case of a Lambertian surface, we need a minimum of 3 images taken under 3 different light source directions in order to be able to compute the 3-dimensional structure of the surface. So now, let's go for a slightly more ambitious problem here, which is assume that you know the reflectance model of the surface. Remember, the reflectance model from our previous discussion can be made fairly flexible. It can have a diffuse component, it can have a specular component with a set of parameters. So with a handful of parameters, 2, 3, 4 parameters, you can have a fairly sophisticated reflectance model that subsumes a very large number of materials that we encounter in practice. So let's say we have this kind of a reflectance model, but we don't know the parameters of the model. And so the idea here is we'd like to do the same thing, extend photometric stereo so that we can take images of the object under different lighting directions and then use those images to recover not only the 3-dimensional shape, that is the surface normal at each point, but also the reflectance parameters at each point on the surface. So we'd like to find both the surface normals and the reflectance parameters at each point on the surface. Well, how do we do this? We know that we need more information, more measurements to do this, and that's exactly what we do. We use an array of light sources, a large number of light sources, and today it's actually possible to very quickly switch between these light sources with LED technology, etc., scan the sources extremely fast, and use high-speed cameras to capture the images, and so you can get a larger stack of images, which then can be used to compute both shape and reflectance. So this idea was first explored in this technique called photometric sampling. So here you see the photometric sampler, where the object is placed in the center, somewhere here, and then you have this array of light sources, which are sequentially turned on. Now in this case, also a diffuser is used between the object and the light sources. And the reason we do this is because imagine you have a perfect mirror. We already know that to recover the surface normal at every point on a hemisphere, say for instance, that is a pure mirror, you would need an infinite number of point light sources. However, if we can convert our point light sources into area sources that have some kind of a radiance distribution, brightness function on top of it, then a smaller number of measurements can be used to fully recover even a specular surface. And that's why one uses this diffuser here. When you turn on one of these light sources, the diffuser creates an area source with a certain function, radiance function that is. So let's take a look at an example. Here's an object that's simply placed in the photosampler. You can see that the top part is diffuse, it's painted, and the bottom part is specular. It's made of a metal, it's specular right here. Now the system has no idea what it's looking at, and it just takes the set of images under different lighting conditions, and then it's able to compute the surface normal at each point. So here, the surface normal is being color-coded for visualization purposes. Red corresponds to a surface normal pointing in this direction. Blue corresponds to a surface normal pointing in this direction. And then you have all the normals in between. And so purple in this case corresponds to a normal that's pointing back at you. So you can see that the three-dimensional structure has been recovered very accurately. Once again, I should remind you that we don't know that the top part is diffuse and the bottom part is specular. The system is able to recover the shape, and you can see the surface normal directions changing gradually in one of these grooves in the screw area right here. And along with this, it also is able to compute for you the reflectance properties of the object. So what this map is telling you is that the system has been able to find that the top part is diffuse in reflectance and actually uniform in terms of its reflectance properties. So the color red is being used for diffuse, and the more red it is, the more diffuse it is. And here you have the specular albedo, so to speak. So this is telling you blue is being used to show that the object is specular. So the darker the blue, the lower the albedo, the brighter the blue, the greater the albedo, and the same applies to the diffuse surface as well. So this method of photometric sampling demonstrates that one can use a more flexible reflectance model and be able to compute not only the surface normal at each point in the surface, but also the reflectance parameters. That tells you what the material properties are. And here is another system which is based on the idea of photometric stereo or sampling. This is the light stage, which was developed by Paul Debevec's team. So the light stage uses a very large number of light sources, as you can see here. And you're talking about a different scale altogether. You can have a person stand inside the light stage. And each one of these light sources is an LED light source. So you can control the brightness very precisely, the color, and also the duration that it's on. So unlike incandescent light bulbs or fluorescent light bulbs, LED light bulbs are light sources are highly controllable, and therefore one can very quickly turn on and off these light sources to scan, capture images of an object under many different lighting conditions very quickly if you use a high-speed camera along with this. So this can be used for what's called relighting. So here you see a person sitting inside, and the person doesn't have to actually sit still. They can be moving around or talking, so it's a performance of some sort. But for each short amount of time, let's say 30 milliseconds, usually video is produced at 30 milliseconds, every 30 milliseconds, but within that 30 millisecond duration, you can actually turn on and off many different light sources and use a high-speed camera to capture multiple frames. So within this one unit of time, you have information related to the person seen under many different lighting conditions. So this is what the high-speed video would look like. You're seeing that the light sources are being scanned extremely fast. And once you have this information, you can take linear combination of these different images within a short duration in order to predict what this person would look like under any arbitrary illumination. So that's what's being done here. You can see that these are three different lighting conditions that the person is being dropped into, and their appearance is made consistent with the environmental lighting by simply taking linear combinations of images that were captured using the light stage. Now, since you have all of this information, you can of course also compute the surface normal at each point for each so-called frame. And so that's what's being shown right here. You have a person, and the surface normal is color-coded as before, using both using red, blue, and green. And here you see the reflectance properties being computed as well, in particular, the diffuse albedo. So once you have the three-dimensional model and you have the reflectance properties, you can literally drop this person in any environment And in this particular case, the environment has this lighting. The lighting is being shown in this tiny little circle here. And so that's the lighting of the environment, and you can render them under that lighting because you have all the information needed to do so. So that's relighting.